Next thing to discuss after we went through numbers and we extended our knowledge of numbers is functions, and after that derivatives. So a function is a mapping. We have a number x, and to that we map the number fx. Like we were discussing complex numbers earlier, so it totally can be that this x is actually an element of the complex numbers. So in this case, we call this a complex function. So earlier we discussed that, I mean, like if in this case, I think we should just go with x to be a real number. So these are going to be the real functions. And that means that we have a real axis, and to that we map certain numbers. So that was our real axis. We had a 0 in it, a unit in it, and this was the y-axis, x-axis, and in here there is something function fx understood. So in physics, what we are usually interested in is the change in a function, and those are essentially described by derivatives. So if I am interested in the change, that what we can look at is the change in the x direction and the change in the y direction. So if I look at the little change in the y direction, which is not dy, and little change in the x, that's going to give me slope of this function. And then if x is a small number, or dx is a small number, then this is going to give us the definition of a derivative. So I say that dx goes to 0. Then and this is the derivative of the f function, right? So I said that the y equals to fx. So that's something which is changes happen all the time in physics. So this is something which is very relevant to anything which we do in physics. The next thing that is very relevant in physics is to approximate a function. So for approximation, we use something which is called a Taylor expansion. Taylor expansion or Taylor series. And that says that my function fx is going to be expanded around a number, let's say a. If x is a, then it's going to be an infinite sum to infinity from n equals 0 of the nth derivative of the function evaluated at this value a divided by n factorial multiplied with x minus a and to the nth power. So what we're doing here, we're interested in how the function looks around at this point, actually that's 1. So let's look at it at this point. That's my A. And then, like, essentially we are zooming into this point. That's going to give us by this expansion. There is a special case of this. Special. If A is 0, then the whole thing is called the Maclaurin series. So that's a bit nicer because then it's just going to be the n power of x instead of x minus a. So let's do an example, and this example will be the sine and the cosine functions, and then later we can do exponential as well. So let's just approximate sine at around, well, so we want a to be around 0. So if a is around 0. Okay, so what do we do in this case? We have to look at the situation when n equals 0. So fn is just going to be the sine if the zeros derivative, if we look at the zeros derivative. So sine x evaluated at 0 is going to be sine 0, which gives us 0. So from this, the whole term just gives 0. If n equals 1, that's the first derivative of the function. Derivative of sine is cosine. Cosine 0 is going to give me 1. So what we have here is 1 over 1 factorial multiplied with x to the first power. So that gives us x. Then when n equals 2, the second derivative of sine is the first derivative of cosine, that's minus sine. But in 0, that just gives us a 0, so the whole factor here is 0. When n equals 3, then we're deriving minus sine, so that's going to be minus cosine of 0. Cosine 0 is 1, so this gives us minus 1. So from that, we have minus 1 over 3 factorial x cubed. And then if I look at number 4, the fourth derivative of sine is the derivative of minus cosine, which is a minus sine, but we already did a minus, so it's just going to be a plus. Sine around 0, or at 0, gives us 0. This term is again just a 0. So we have x, and then we have minus 1, 3 factorial, x cubed. And then you can see that now we go back to this point. So again, the next term is going to be 0, and then the next term is going to be coming with a plus 1. So that's plus 1 over 5 factorial of x to the fifth power, and so on. So this whole technique is actually the way how your calculator actually calculates a number in sine. So when you put sine 0.2 to your calculator will actually sum up these powers of x to a certain degree. So we could do the same thing with cosine x when we are around 0, x is around 0. So it's going to be very similar in the calculation, but the trend will be a bit different. So n equals 0, that's just the um, function itself, that's cosine 0, so that gives us 1. So we already know that, and then we divide with 1. So from this it's 1 over 1, 0 factorial, right, which is by definition 1, multiplied with x to the 0's power, which just gives us 1. So we already can write this is going to be a 1. N equals 1, that's the first derivative of cosine is a sine. Whatever the sign here is before the sine function, that is going to give us a 0. Anyway, the derivative of cosine is a minus sign, so but whatever. So next step, n equals 2. That's the second derivative of our function, which is going to be derivative of sine is cosine, so it's a minus cosine at 0 gives us minus 1. So that gives us minus 1 over 2 factorial multiplied with x to the second power. This was here multiplication as well. So I have minus x squared over 2 factorial. Next term is just going to be the derivative of cosine, which is a sine evaluated at 0 gives us a 0. Then next term, the fourth, f4 is going to be a derivative again, which is well, okay, so I was not writing it here, but this was derivative of this is a plus sine 0. So derivative of plus sine is going to be a cosine at 0, which gives us a plus 1. So from this, we have a plus 1 over 4 factorial x to the power of 4. So plus x to the power of 4 divided by 4 factorial, and so on. So if you compare these two, we see that the sine goes with the odd numbers, the cosine goes with the even numbers on the powers of the x. And then if you look at a third example, which is going to be the exponential function. So the exponential x is an easy thing because the derivative of the exponential is just going to be the exponential itself. So when we evaluate, so n equals anything, any is the exponential, and when we evaluate that at 0, that just gives us 1. So all of these terms are going to be plus 1s. So this is going to be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. So we discussed in last time that in the Euler identity we had so a reminder that the Euler identity says that a odd I some angle is the same as cosine of the angle plus I times sine of that angle. So if I put I here, then what's going to happen with this expansion is that if n is even, then there are going to be -1 factors. And if n is odd, then we just have I, right? Because I to the nth power is going, any odd power is going to be I again, or -I. So with that, we see again that, okay, so the cosine, this term, the one in the exponential, is coming from the cosine term from here, and then we have an x term which comes from the sine first vector in the or the first term in the sine, and then we have the x squared over 2 from here. That's the same as this term, and then the cubic term is coming from the sine. So with this Taylor expansion, we showed that this is indeed true. Okay, then A is just almost x, but it's a little bit off from x. So how does my function f, x plus epsilon, look like when we approximate it? It's if I look at the function close to x, then it's actually going to be very similar to the function at x itself. And then we add the change in that function with in the change in the x. So that's going to be denoted as the derivative of f by x. And then we will have terms in which we have epsilon squared. And so as for most of the things in physics, or at least we say that in a first approximation or a first order, we don't care about anything which goes with epsilon square. So this O is called the big O, or the ordo notation, which means that we don't care about the terms that go with epsilon square. So we will approximate functions, like this changes in functions with the function itself, and then adding the epsilon times the derivative of that x. So actually, there is some other notions for derivatives. So I could write this whole thing as fx plus epsilon, and then this kind of a derivative notion of x, and then plus again the ordo epsilon squared. Let's move in the direction that what if I have more coordinates? So that's like very relevant in physics. We don't have just one coordinate in physics in this, when we discuss like space-time or something like that. So if I have an f function in which the x coordinate I move with epsilon x, and in the y coordinate I move with epsilon y, then this is going to be approximated as the function at f xy plus epsilon times the derivative of f by, well, actually, let's just go with the x first, epsilon x, derivative by x, plus the epsilon y times the derivative of f by y. And then, again, we say that, oh, there are terms with epsilon squares, which I am ignoring right now. And I think that's all we need to really know right now for Taylor extension.